There are moments in mobility design when a vehicle stops behaving like transportation and begins behaving like infrastructure. Standing before this machine, I'm not looking at a motorhome in the conventional recreational sense. I'm looking at a rolling architectural thesis on autonomy, structural ambition, and luxury mobility redefined at infrastructural scale. Before we go further, it is important to clarify that what we are examining here is a fictional, AI-generated concept study, a speculative design exercise created for exploration and imagination rather than a real-world production vehicle. That distinction matters because it allows us to analyze this machine freely, as a thought experiment unconstrained by current manufacturing limitations, while still grounding our discussion in engineering plausibility. Now let's begin with proportion. From a dimensional standpoint, this motor home appears to extend approximately 14 to 16 meters in overall length. The wheelbase, or more precisely, the distributed wheelbase across its triaxle rear and dual front axle configuration, suggests a platform engineered for extreme load-bearing stability. Height likely approaches 4.2 to 4.5 meters, especially with the integrated rooftop deck and equipment modules. Width appears near the upper legal boundary for heavy transport vehicles, likely around 2.6 meters. But proportions alone don't tell the full story. What's more compelling is the stance logic. This vehicle sits low for its apparent mass. The ground clearance is controlled rather than excessive, suggesting a suspension philosophy oriented toward highway composure and load-leveling air systems rather than rock-crawling articulation. The 6 rear wheels, arranged in a triple-axle configuration, indicate weight distribution optimization for a structure of this mass and likely support for rooftop occupancy and heavy onboard systems. From an engineering standpoint, this solves 2 primary challenges. First, it distributes vertical load more evenly across the chassis, reducing per-axle stress and improving braking stability. Second, it enhances directional stability during crosswinds, a critical consideration given the tall glass architecture. Now, let's examine the surface language. The exterior skin is layered and faceted, almost parametric in execution. There's a deliberate tension between armored geometry and aerodynamic smoothing. Notice how the front fascia transitions from sharply creased upper brow elements into fluid lower intakes. This suggests airflow management designed to split high-pressure frontal air, channeling it around the cabin rather than allowing stagnation zones to build. The windshield curvature is particularly significant. It wraps with a subtle compound curve, not a flat pane, which reduces drag coefficients while improving panoramic driver visibility. Structurally, a glass-to-body ratio this ambitious would require reinforced A-pillars with likely high-strength boron steel or carbon composite internal framing. In real-world production, such glass expanses introduce torsional rigidity challenges. The structural implications would demand either a semi-monocoque exoskeleton or an integrated roll cage architecture hidden within the body cladding. The paint finish deserves examination. The metallic matte composite tone, a brushed titanium aesthetic, suggests either vapor-deposited ceramic coating or multi-layer nanopigment paint with thermal reflectivity properties. On a vehicle of this scale, thermal management isn't cosmetic, it's operational. Reflective coatings would significantly reduce solar heat absorption, lowering HVAC energy demand. Observe how light diffuses across the contoured surfaces. The transitions are smooth yet intentional, implying digital surface modeling with curvature continuity control rather than traditional stamped panels. Panel seams are minimized and integrated within sculptural lines, reducing aerodynamic interruption. Lighting identity is where this concept reveals its maturity. The front DRL hierarchy is horizontally stratified. Upper marker lights establish width perception. Mid-level narrow LED strips create a technical signature. Lower matrix headlights are recessed within aerodynamic housings. This layered approach communicates both scale and technological authority. At night, this vehicle would not simply be visible, it would be architecturally legible. Now consider the wheels. These are not decorative alloys. They appear reinforced, beadlock-capable units with high-profile, all-terrain tires. However, the sidewall height is balanced, not exaggerated, suggesting a bias toward long-distance touring rather than extreme off-road articulation. From a load perspective, 6 rear wheels significantly improve contact patch area. In real-world use, this would reduce road surface pressure and enhance braking redundancy. Let's move upward. The rooftop deck transforms this vehicle from transport device into mobile architecture. There are visible solar arrays integrated flush into the roof plane. Satellite communication domes and likely LiDAR or autonomous sensor arrays are positioned at elevated central points for optimal signal and detection range. Structurally, supporting rooftop occupancy requires reinforcement beams running longitudinally through the chassis spine. This adds weight, but in a hydrogen-electric hybrid configuration, which we'll discuss later, weight distribution can be actively managed. The rear identity continues the aerospace theme. Lighting is symmetrical and horizontally oriented, visually widening the stance. Air exit channels are subtly integrated along the upper rear fascia, implying pressure relief and thermal venting for battery or hydrogen storage systems. Now let's interpret the philosophy. This concept does not merely compete with conventional Class A RV architecture, it redefines the category as a mobile luxury observatory. There are marine influences, particularly in the rooftop deck configuration. There are aerospace cues in the faceted body surfacing, and there is architectural restraint in lighting integration and material layering. The intended user archetype is not the casual camper, it is the autonomous explorer. Someone who values independence, technological integration, and elevated perspective, literally and philosophically. My first professional impression. This is not a fantasy vehicle. It is a serious speculative mobility study that challenges assumptions about structural scale, luxury positioning, and energy independence. It feels mature in design language. Aggressive but not chaotic, imposing but proportionally disciplined, and that discipline is what makes it believable. Even without stepping inside, the exterior engineering allows us to logically construct the interior architecture. Given the roof deck and visible height, we are likely dealing with a split-level interior. A lower chassis-integrated systems deck housing battery modules, hydrogen tanks, gray water storage, and structural reinforcement. Above that, a primary living level, possibly even a raised forward cockpit loft. Ceiling height inside would likely exceed 2.2 meters in the main living corridor. The tall glass panels imply panoramic lounge seating aligned along the midsection. From a load path standpoint, weight-heavy components would be centrally located between axles. Sleeping quarters would likely be positioned toward the rear, where vertical oscillation is reduced compared to the front axle. The sleeping environment would need acoustic isolation layers within the wall panels. Multi-density insulation foam combined with laminated acoustic glass would reduce highway resonance. Privacy could be managed through electrochromic glazing. This would allow tint density adjustment dynamically, balancing openness with thermal control. In the kitchen zone, compact efficiency would dominate. Induction cooktops reduce open flame risk and integrate seamlessly into composite countertops. Water systems would require multi-stage filtration and possibly gray water recycling loops for extended off-grid capability. From an engineering perspective, water weight management is critical. Every 100 liters adds significant mass. Smart tank placement between rear axles would maintain center of gravity stability. The washroom would likely adopt a modular wet bath concept to conserve spatial efficiency. Vacuum-assisted water-saving toilets could reduce consumption dramatically. Ventilation would integrate roof-level exhaust channels, possibly heat recovery systems to minimize thermal loss. Now to the cockpit. The forward visibility is commanding. The glass expanse allows a near-panoramic driving experience. An augmented reality heads-up system could project navigation overlays directly onto the windshield. Semi-autonomous driving is plausible in such a platform. Given the elevated sensor placement and radar integration, highway autonomy could be supported, though urban maneuverability would require advanced steering geometry due to the vehicle's length. Energy strategy is perhaps the most intriguing element. A hydrogen-electric hybrid system makes conceptual sense here. Hydrogen fuel cells could provide extended-range energy generation. Battery modules would manage peak load capture and regenerative braking capture. Solar roof contribution would not power propulsion independently, but it could sustain auxiliary systems, climate control, lighting, communication during stationary periods. From a real-world engineering standpoint, current hydrogen storage density remains a limiting factor. Advancements in solid-state hydrogen storage or higher efficiency fuel cells would be necessary to make such a system viable at this scale. Climate zoning would be critical. Given the glass area, independent HVAC zones would manage thermal gradients between cockpit, living area, and sleeping quarters. AI environmental adaptation could monitor sunlight exposure and automatically tint glass, adjust ventilation, and redistribute loads. For long-distance touring, this platform excels in theory. The multi-axle stability and onboard energy generation would support